Thank you. Yes, so I'm Florent Gravin, head of technology at Camptocamp. And at Camptocamp, we are a company really specialized on open source geospatial softwares. And we are deeply involved in many OSGeo, so it is the organization for open source and geospatial pillars, solutions such as GeoServer or open layers or stuff like that. So if you do maps, maybe you have heard about that. And yes, last year I came to this conference where it's not really about geo. We always go to geospatial conference, and it was the first time. And why this talk? Because last year I really missed the geo part of the data. So we are talking about the data, and we know that there is a lot of data that are geospatial. So I propose a talk to bring the geospatial aspect of the data, and here what I'm there. So last year was a little bit flat, and I tried to bring some coordinates, 1, 2, and even elevation and third dimension to the conference. So geospatial processing. I will start with a use case that we had recently to illustrate what we can do with geospatial data and what processes. So we have been asked to process Meteo Swiss data, so rain data, for instance. And we wanted to see just for 3 days rains, which buildings have been impacted by heavy rains. So just an example. So how we did that? So we had to download a GeoTIFF file, so the files for the rain, where 1 pixel is the amount of rain per pixel. Then we have to load all the files in a multidimensional array. So we use libraries, Python libraries like Xarray, raster.io, and so on, to build yes, a multidimensional cube. Then we needed, it's a summary. Huh? So then we needed to clip that on the Switzerland boundary, which is a GeoJSON file. And we processed every image, so to make filters, squares, or grids, 3-3 grids, to extract really the value of the rain on every area. And then we started to aggregate all these pixels by so 2 methods with threshold and with blobs. And then we loaded the buildings from Overture maps, and we did an intersection on the buildings and the blobs. So these are, for instance, all the 3 days rain on the Swiss. Here it's the threshold method. So we check over 10 centimeter, over 50 centimeter, over etc. etc. And then it's the intersection with we see the building, the blobs, etc. And then we can have some visualization tools. So then we produce a data. So the pipeline did produce GeoJSON, and then we have tools to bring the data to build value out of the data and to share the value. So it's just an example of an open source tool that allow you to quickly style and visualize and get insights from your use case. So the geospatial stack. What is about specifically about geospatial? So as I said, there is a urban myth. I don't know if it's proven somewhere, but 80% of the data have a spatial component. So it means that they have coordinates, or they could have coordinates. Yesterday I saw a talk with Meteo, and they were talking about city, Paris. We can always affect a position to Paris, a point or polygons or whatever. And we are lucky because in the data ecosystem, also most of the tools are geospatial. So for instance, Arrow, there is GeoArrow, Parquet, there is GeoParquet, GeoPanda, DuckDB has a spatial extension, PostGIS, there is very famous PostGIS. So almost all the data have a geospatial component, and all the tools that you are used to use daily with dealing with the data, they also have a geospatial component. And it becomes more and more trendy and more natively supported. So what does it mean to have a spatial component? It means there are two things. So it means that there is a geometry. So your system or your library, it should handle the storage of the geometry. It could be GeoJSON or WKT, WKB, binary geometry. And the system could also provide compute operation, like all ST underscore function that comes from PostGIS, but have been ported to many other data systems, like BigQueries, DuckDB, and so on. So it's function to be able to process coordinates and to do stuff with coordinates, like intersection, like buffers, like clipping, like many others. Yeah, so it's a quick video on, for instance, it's tools that you can have the habits to use. It's a Parquet file, so it's Overture maps data, so that have been heavily processed and published as Parquet. And it's DuckDB WASM, so it's tools that yeah, you are very familiar with. And I used just the special components of those tools to build this kind of insights, where you can directly build a SQL query on top of cloud native data to be able to see the distribution of places over administrative boundaries or over hexabin and so on. So what is different with Geospatial? The characteristic, I will say that there is a lot of big data, okay, but a geospatial data is often big because of its coordinates. So a point, it's okay, but when you have polygons, there is 1 point per vertex, and it could be very huge. Then there is many formats, different formats. When you deal with tabular data, you have JSON, CSV, and maybe others. But when you deal with geospatial data, there are many proprietary formats like shapefile, and there is also a lot of different formats that you need to deal with. The compute is very expensive because when you do aggregation on tabular data or a mean or whatever, it can be fast because it's numerics, numbers. But when it's coordinates, it's very longer and heavy to process an intersection, for instance. And yeah, the quality also is harder to predict because you need to check the coordinate, etc. So those bring new constraints, and I think it brings the need of more power globally. So here, what a pipeline looks like. So it's same as other pipelines, but for instance, you need to ingest the data. So what you saw from my example, the first thing I did is I downloaded the data. So through the different APIs or buckets or whatever. Here I mentioned STAC because STAC is an API which is geospatial, will helps to find geospatial assets and data sets such as imagery, but also Parquet files. And I mentioned Overture maps also because many pipelines or many processes, they use OpenStreetMap data or an extension of OpenStreetMap, Overture Maps data, to have worldwide data. Then you need to control, like, is the projection okay? Is the encoding okay? Are the coordinates valid? Is there integrity within the geometries, within the data? And the transformation aspect, it's often like you want to reproject, you want to change the format. So the projection, it could be, yes, Mercator spheric, it's the Google projection on Google Map, but you can have degrees projection, you can have local projection. So it's a heavy work on transform, the projection, the coordinate systems. You need to convert the format, and you need to compress the data and build a special index. Because the index is really where the processing, it's really something really important to make the processing efficient. I will talk about it later. And load, it's the same as other ETL pipelines. So how to scale these pipelines? The example I show is just Python script, and you can run it in QGIS with the QGIS modeler, but it's local and it's not really error proof. So first, I would say that cloud native formats, geospatial cloud native formats, help to improve the capacity, the efficiency of the pipelines, because they are optimized for cloud storage and cloud computing. So it means that I don't need to download all the data anymore. So for instance, Planet or Sentinel data, they are everyday billions of gigabytes of data. So if I have to download all the files, it could be very long. So one idea is to keep the data at one place and to process it on the cloud, to store it on the cloud, and now to process it on the cloud. So it's thanks to cloud optimized format, for instance. So the characteristics are you can just do partial reads with HTTP range request. So you can parallelize processing, and you can just read a little part of the file, so on a specific extent. And it's what is really important, because if you want to work on a small area, you don't need to download the whole file, and it's where the breaking change is. So the most famous one is the cloud optimized GeoTIFF. So it's a standard GeoTIFF, but yes, with range request, etc. So it means that now you don't need to copy the file to download, and you can stream the data and process them on the flow. So there are other kind of formats for raster data, but also for vector data. So it was hard to find and to build such formats because, for instance, Parquet, there was no geometry, etc. So there are different candidates. But now GeoParquet is quite used. So all this format helps to make pipelines. And it is true that even the example where I directly fetch GeoParquet from the viewer, those formats are more meant to do processing and not for the visualization. And it's really where it shines. So we scale with the formats. Now we scale with the processing. So I can have a Python script, but is it enough? What is my pipeline? How big are my data? How many processing should I do, etc., etc. So it's hard to choose the right tech. And you know that you can go for a single node Python script to a cluster with Spark and cluster processing, like with Sedona or GeoMesa. Sedona really helps to process billions of geospatial operation on clusters. And now even Iceberg. So we are talking about open format open table formats. And Lake House, and now Iceberg also support natively Geospatial, so you can really build your system, your pipeline, your warehouse, even if you have a Geospatial component with the same stack. The scaling, so yeah, so it really depends what you need. You don't have to bring the cluster thing if you just need small operations. So it's very important when you draw your pipeline and you design your pipeline to know what you want to do. So you have different solutions like the other pipelines which are not geospatial, but PostGIS, if you need transaction consistency, etc., live data. If you have a lot of tabular data and you need compute, but you don't have the geospatial aspect is not very important, like you are not really doing operation on big coordinates geometries. You can use OLAP system as a DuckDB, but if you really have millions of objects with, you want to perform millions of spatial joins on geometries, then you should use processing engine like Sedona or Databricks. Just mentioning this one because it's new. So Sedona, it was a cluster, and they just lay out where robots company went out this Sedona DB. It brings the capacity to process spatial data, but you don't have to install it on a cluster. So you have a lot of choice to build your pipeline. Now I talk about the spatial indexing. It's really important. So on the left, it's a classical R3 index. So it means that there are squares, extent, and you know if a geometry or a point is inside this square, and then you go down in more little squares, and it helps the system to know if geometries are contained, are close, are etc., or intersect. And for instance, in Parquet, the issue was we can store the geometry as binary in the column of a Parquet file, but it's really hard to have a correct index. So the only index in V1 was just the extent. There was a metadata in every geometry, and there was its extent, and you had to perform a query where you say x mean superior to the extent, etc. So you had to browse a lot of useless data to be able to find the intersected data. So now it changed, and the idea is to use the ability of the rows, the page, and the column of Parquet to organize the data by location. So it means that you can skip a lot of rows because you instantly knows that they are not in the correct square, for instance. But maybe there are specialists there about that. So it's very important because if you don't have a good index, your compute will be bad. So it's really important. Now that you've built your pipeline, you have output data. So in my example, I have GeoJSON. I just loaded GeoJSON, but if you have a lot of data and you want to do visualization, GeoJSON can be very heavy to deal with on the browser and to load. So usually you provide your data through tiles. So you can have vector tiles or raster tiles and OGC standards to be interoperable with all of GIS system, like GeoServer Cloud, help to provide all the OGC standards from your data. This is an example of INSEE, so a statistic office in France, and yes, with vector tiles, they have all their pipelines, and the end user can visualize very quickly all the data thanks to these formats. A mention to Cloud Native Foundation because I think that they have helped to push forward all this technology to be able to build bigger and more reliable pipelines, geospatial pipelines. They push for new formats, new cloud native formats, and they foster innovation on the geospatial aspect of all the warehousing, the processing, the formats, and the libraries. So it's the end anyway of the presentation. So this is the geospatial data stack landscape provided by Matt Forrest, which is really famous in this ecosystem. And so yes, if you want to build geospatial pipelines, you have everything here. Just mentioning, so the cloud native format I talked about here. Then the cloud storage, so you can store on block storage, you can store on PostGIS, etc. The processing, OLTP, OLAP, and processing, what I've talked about. The transform, so GIDAL is very important in the geospatial ecosystem, and it's at the base of every transformation and so on. You can see that you have some spatial indexing like H3, A5, etc. DBT, it's not geospatial, but there is geospatial support. So there is a very large ecosystem. Many of the applications are open source, so you can use it and integrate them in your pipeline. You see there is a lot of Python tool and Python library to deal with geospatial data, and you have QGIS for sure, and some libraries for the visualization. What I didn't talk about, if you want to operate in production those those pipelines, you need to be able to monitor and to orchestrate your batch. So instead of just having a Python and cron on a computer, you really need to use something like Airflow to be able to know what process, what resource that it use, could you prioritize process, you can stop them, is there error, etc. Because when you rely on a full pipeline, you really need to be sure that in the end, all the steps have been successful. Yes, last text slide from Carto. So yes, if you need to jump into Geospatial, you have many resources here, how to operate and process geospatial data. And so to conclude, I think that Geospatial is no more a niche. It means that every data is geospatial and every pipeline integrates more and more geospatial data. And all the technology and the libraries natively support more and more geospatial formats. So it's great. If you want to build a pipeline, you really think of how to scale it. Go small and then grow and scale if you really need it. Don't install Sedona for a small operation. And try to build production-ready pipelines with orchestration, monitoring, error management, etc. And I will just thank all the amazing geospatial community, all those guys who have ported geospatial things to Arrow, to Parquet, the foundation, Geospatial Foundation, because I think it's a really exciting moment in the geospatial world. And there are fancy new stuff all the time, and it's very exciting and promising. Thank you.
Thank you, Florent. So, do we have questions? Yep. Sorry, starting from Anita. Sorry.
Thanks so much for the great presentation. Since you mentioned STAC, I was wondering what's your opinion on STAC for vector applications? Do you use it for vector data as well? Because in my mind, it comes from the EO community and is probably more targeting raster.
Yes, so there is a debate in Geospatial with STAC and, for instance, OGC API features or OGC API records. One thing is if the geometry is a metadata, use STAC. If the geometry is the data, use OGC features or records. But so it means that yes, it's more for spatial temporal assets, so like satellite imagery on a space at a certain time. So for instance, I don't know, cycling past vector dataset, it doesn't make sense. But now I also found it useful. So for instance, the Overture Maps data, they are provided as Parquet files, and there are hundreds and hundreds and hundreds of Parquet files. So if you want to just fetch the correct Parquet files on your web front-end applications, for instance, they wanted to provide them as a STAC catalog for GeoParquet files, and I think also it's a very good idea of using that for vectors.
Thanks.
Thanks for the great talk. Are there practical limitations on the size that cloud-optimized GeoTIFFs can or should get to? I know for storing Sentinel-2 data, they have the tile grid that they use where they split it into 110 kilometer by 110 kilometer chunks. But is there a practical spatial or resolution or grid size that, or a limit that these file formats can reach?
I don't really know, I have to admit. For me, the goal of this format is that you don't have to make a mosaic or to split, is that you can have a big file. I know that, for instance, in France, people, when they aggregate data, they build a mosaic and then they build a huge cog out of it. I don't know if it's very efficient. I'm not specialized in the raster processing. I don't know if maybe other one has the answer, but.
Other questions? Nope. Okay, so I think we can thank again our speaker.
Thank you.